Hello everyone. Today I am going to explain about arithmetical instructions in 8086. So these are the various arithmetical instructions which are performed by the 8086 microprocessor. That is addition. The corresponding instructions are add ADC. That means add with carry. Subtraction. That is subtraction and subtraction with borrow. Multiplication, that is mul and imul. The imul is used for the signed bit multiplications, signed numbers multiplications. Division or I division, that is also for signed numbers division. Increment, INC. Decrement, DAC. Compare, CMP. Okay, BCD operations, binary coded decimal operations, that is DAA. DAA is decimal adjust after addition. Similarly, decimal adjust after subtraction. And ASCII operations, that is ASCII adjust after addition, ASCII adjust after subtraction. Okay, so these are the various instructions. These are the various instructions under arithmetical category, arithmetical instructions category. Now let us discuss one by one instructions. Okay, add instruction. It is used for to add two operands. Okay, two operands. Two operands means that is immediate number can be added with the register. Similarly, immediate number can be added with the memory location, and register number can be added with the register, and the result is stored in the destination position. Okay, that means this is the source operand, this is the destination operand, and source operand is added with the destination, and the result remains available in the destination. Similarly, immediate number is available in the immediate number, it is the source added with the memory location contents. Similarly, register contents are added with the register. Okay, but the immediate number plus immediate number is not possible. Okay, immediate number plus immediate number is not possible. It is invalid instruction because this is the source. Okay, but this is the destination. This is the destination, but here the destination should not be a immediate number. It should be one location, that is either memory location or register to store the data. Okay, so immediate number plus immediate number is not possible, not valid. Okay, so for this, what is the instruction? Add al comma, for example, 28 hexa. Add al comma 28 hexa. That means 28 number is added with the al register contents, and the result is al. Result is stored al plus 28 hexa, hexadecimal number. Okay, this is hexadecimal number. That is the immediate number. Similarly, immediate number can be added with the memory location also. Okay, that means add memory location. Memory location, already I told you, in any one of the addressing mode, memory addressing modes, we can describe. Okay, so ds slash 28 hexa. Okay, then what does it mean? Memory location contents are added with the memory location contents are added with the 28 hexa. Okay, this is immediate number, but memory location effective address is available in the data segment register. That is the meaning of this. Okay, and similarly, register plus register means simply add al comma bl or add ax comma bx. 16-bit addition, 8-bit addition, 16-bit addition, 8-bit addition, all this is the 8-bit addition, this is 16-bit addition, and the result is stored in the destination register. The result is stored in the destination register. Okay, suppose if in these instructions or in this type of addition, if any carry is generated, then what happens? We have to use the add with carry instruction. add with the carry instruction. Okay, that means in between any auxiliary carry is added, in between any auxiliary carry is generated, then that add with the carry instruction is used. Okay, for example, here suppose add AL comma BL 0 1 1 1 0 1 1 0 1 0 0 1 0 1 or 0 0, for example. So then what happens? This is 0 addition, this is 0, this is 1, this is 1 0. Okay, this is what happens. This is 0 1, this is 0 1, this is 0 1, this is 0 1. That means here the carry is generated. Okay, but in between any positions, auxiliary carry is generated. Suppose this is the addition, but after this addition the carry is generated, but in between the carry is uh, the carry is also generated. Okay, the carry is also generated, and it should be passed from the position to next position. In these cases we have to use the add with the carry. Okay, or simply if we are using 0 1 1 0 1 1 0 1, or this is 1 0 0 1 0 0 1 0, then what happens? So simply 1 1 1 1 1 1 1 1. So here no carry is generated from one position to another position. That means no carry is generated from one position to another position. That means no need to. It is a simple addition. This is a simple addition. So add instruction. But here the carry is generated from one position to another position. Then the ADC instructions have to use. Okay. Similarly, subtractions also. Similarly, subtractions also. Similarly, subtractions also. For example, sub AL comma BL, sub AL comma BL. For example, if AL equal to 78 hexa, okay, BL is equal to just 23 hexa. Okay, then what happens? It is the biggest number and the smallest number, and simply the subtraction can be done. Okay, subtraction can be done. But whereas 75 hexa and for example 27 hexa, here a borrow situation is generated. Okay, a borrow situation is generated at this at this moment we have to go for the subtraction with the borrow. Okay, subtraction with the borrow. When the subtraction is going on, that means the largest number minus the smallest number, there is no need of the borrow. Then we can use directly sub instruction. When we are subtracting, that is the smallest number minus biggest number, then you have to go for the subtraction with the borrow. Here the borrow operation is required. Okay, next one is the multiplication instruction. Multiplication instruction. Okay, multiplication instruction. Here one point is to be remembered here during for multiplication instructions, that is the syntax for this is, suppose if we want to perform EL contents are multiplied with the BL register contents, then the my instruction is multiply BL only, not multiply AL comma BL. Okay, because in the multiplications and division instructions, multiplication and division instructions are performed between any two operands, but out of these two operands, okay, out of the two operands, one of the operand compulsorily, one of the operand is compulsorily in the accumulator. Okay, accumulator. One of the operand compulsorily should be available in the accumulator. So that's why one of the operand by default it is from the accumulator. So that's why we need not to specify this in the instruction. So only the second operand should be specified in the instruction. Okay. For example, multiply 18 hexa, for example. Then what happens? By default, here the multiplication is AL star 18 hexa can be done, and the result, suppose this is the 8-bit number multiplied by 8-bit number. This is one 8-bit number multiplied by 8-bit number. The result will be the 16-bit number. The result will be the 16-bit number, and this 16-bit number, 16-bit product, 16-bit product or 16-bit result is available in AH-AL combination. Okay, AH and AL combination. In the result, the lower 8-bit of the result is available in AL, and upper 8-bit of the result is available in the AH. Suppose this is 8-bit multiplication. Suppose if we go for the 16-bit multiplication. Okay, if we go for the 16-bit multiplication, then what happens? 16-bit multiplication, then what happens? Multiply bx, for example. Multiply bx. Then what happens? It results ax multiplied by bx. Ax multiplied by bx. So 16-bit into 16-bit. Okay, that means 16-bit into 16-bit. 16-bit into 16-bit means the result is the 32-bit. Result is the 32-bit. So this 32-bit result is available in the two 16-bit results, two 16-bit registers. That is lower result, lower 16-bit is available in the AX register, and a higher order 16-bit result is available in the DX register. So DX AX register pair. Okay, DX AX register pair is used for to store the 32-bit of the product. 32-bit of the product. This is about the multiplication. Okay, so multiplication, simply only the second operand we need to give. The first operand is by default, it is from the accumulator contents. First operand by default from the accumulator contents. Okay. And I multiplication it is purely for the signed bit number multiplications, and the same concept is same, but it is for non unsigned bit operations, that is for signed bit operations. Okay, next one is the division instruction. Division instruction also, there is a 8-bit division, there is a 8-bit division and 16-bit division. 8-bit division and 16-bit division. Okay, 8-bit division means, actually division means what? Numerator divided by denominator. Okay, numerator divided by denominator. In case of 8-bit division, the numerator is the 16-bit number, denominator is the 8-bit number. Okay, so this 16-bit number compulsorily should be available in AX, and 8-bit denominator can be a 8-bit denominator can be a either register contents or memory location contents or any immediate data, immediate number. Okay, next. So for example, AX and results. What is the results? Result of the division. Result of the division is quotient and remainder, isn't it? Okay, quotient and remainder. In case of 8-bit division, quotient is available in the AL register. Quotient is available in the AL register and the remainder is available in the AH register. Okay, that is the about the division. Just a simply example. In this, the numerator is compulsorily it is available in the AX register. So that's why we need not to specify this numerator in the instruction. Only we can specify the denominator. For example, division BL simply. Then what does it mean? AX divided by BL. Okay. Similarly, division 15 hexa. What does it mean? That is AX divided by 15 hexa. That is the meaning of this. Okay. Similarly, 16-bit division. 16-bit division means again this is the numerator divided by denominator. Okay, denominator. The numerator is a 32-bit. Numerator is a 32-bit compulsorily and the denominator is a 16-bit. 32-bit numerator. 32-bit numerator is available in the DX-AX register pair. DX-AX register pair. Okay, divided by any 16-bit register or 16-bit register or 16-bit memory location. Okay, or 16-bit immediate number. Okay, and for this the results are, what are the results? Quotient and remainder. Okay, quotient is transferred to AX and the remainder is transferred to DX. Okay, simply for examples, this is also example. This is also example. So division BX. Simply division BX. Then what does it mean? This is DX AX register pair contains total 32-bit data divided by BX. Similarly, another example. Here, this is also another example. DX division 16-bit number 1532 hexa. Then what does it mean? DX AX register pair divided by 1532 hexa. Okay, that is about the division. And same reminders are available in remainder and quotients are available in these positions. Okay. Next, increment and decrement. Okay, increment and decrement. That means this is used for two increments. It increments the contents of any register or memory location by 1. Okay, it increments the contents of register or memory location by 1. Similarly, decrement. It decrements the contents of register or memory location by 1. Okay, here no immediate data cannot be used because immediate data and here in this increment only one operand is used. Only one operand is used in this type of instructions. This decrement also only one operand. Only one operand is used. Okay, for example, INR INC AL, okay, or INC BX. Then what does it mean? Suppose if before instructions, before instructions, suppose AL is equal to 28 hexa, then after instructions, AL is equal to 29 hexa. Similarly, INC BX, that means before BX is equal to 1532 hexa, then after this instruction, BX is equal to, simply it is incremented by 1, that is BX is equal to 1533 hexa. Okay, similarly, same opposite decrement. Okay, so decrement, it is also, it decrements the contents of register or memory location by 1. In this, the memory location contents also we can use. Okay, for example, INC SI. That means SI register contents. SI register contents. Sorry. Uh, uh, this represents the memory location. That memory location contents are incremented by 1, but here this is memory location contents. Contents are incremented by 1. Memory location effective address is available in the SI register, isn't it? It can be incremented or decremented based on that. Okay. Similarly, here also decrement DAC. Okay. So DAC AL or DAC AX, whatever it may be. DAC SI or decrement like this also. Okay. That is increment and decrement. Next one is the compare instructions. That means it compares the two operands, source operand and destination operand. It compares the two operands, that is source and destination, and tells us which number is the most largest number or smallest number, or both are equal, based on the flags. Okay, based on the flags conditions, it indicates either largest or smallest or equal numbers. Okay, that is the meaning of this. Suppose, for example, compare AL comma BL. I'm giving compare AL comma BL. Okay, for example, then AL is equal to, for example, 55 hexa, and BL is equal to 20 hexa, for example. Then obviously we know AL is greater number. But compare instruction initially performs subtraction instruction. Okay, subtraction operation. It initially performs the subtraction operation, but here no carry is generated, because 55 minus 20, that is, the result is a positive number, not a negative number. Okay, so no carry is generated. That means the AL is greater than BL. Okay, for example, if second case, if AL is equal to 25 hexa, BL is equal to BL is equal to 47 hexa, for example. Then also it performs AL minus BL. But here, then in the after when we are using compare AL comma BL, then what happens? It performs a subtraction operation. That means AL register contents are subtracted from the BL register contents are subtracted from the AL, but result is a negative number. Result is a negative number. That means 25 minus 47. 25 minus 47. Result is a negative number. That means carry generated. Okay, carry generated. When carry is generated, it will tell us like AL is less than the BL. Okay, and based on suppose if third condition, if AL is equal to 20 hexa, BL is also equal to 20 hexa. For example, if we are using compare AL comma BL, then what happens? It performs AL minus BL operation. That means 20 minus 20. It is the result is the 0. Result 0 means 0 flag is set. 0 flag is set. When the 0 flag is set, then this instruction indicates both the operands are same. Both the operands are same. Both the operands are same. Okay. So based on the carry flag and 0 flag, initially it performs the subtraction operation, and based on the carry flag and 0 flag conditions, it will indicates whether the destination operand is greater than or equal to second number. Okay, compare instructions. Next, DAA. This is decimal adjust after addition. After addition. Decimal adjust after addition. Okay. Suppose move AL comma 28 hexa. Move BL comma 43 hexa. Okay. 43 hexa. Then add AL comma BL. Then add AL comma BL. Then what happens here? AL is equal to 28. BL is equal to 43. Then 28 plus 43. Okay, how much it is? 8 plus 3, that is 11. 11 means it is B. 2 plus 4, that is 6. Okay, 6B hexadecimal number. This hexadecimal number is converted to decimal number. Is converted to decimal number. How? Suppose this is first instruction, second instruction, add AL comma BL. Then if we use the DAA. Okay, so then what happens? So when we are using the DAA, this hexadecimal result is converted into decimal number. Okay, by suppose it checks the lower number. Okay, lower number. If it is greater than 9, greater than 9 means A, B, C, D, E, F. Greater than 9 means A, B, C, D, E, F. Okay. So here the lowest position number is greater than 9. So then it will add the plus 6. Okay. So B plus 6. B plus 6 means what? B means 11. Okay. So 11, 12. Sir, B plus 6 kada. So 11 plus 6. That means how much? 17. Okay. 17. 17 means in the hexadecimal how much it is? Hexadecimal, it is 1 1. Okay. So then this 1 here and this 1 position carries goes to here, and 6 plus 1 7. Okay. So now this is 71 is the decimal number. Normally, if we add 28 plus 43, okay, normally if we add 28 plus 43, what is this? 8 plus 3, 11, and this one here, 4 plus 3, 7. 71 is the decimal number. 71 is the decimal number. Okay, so here move AL comma 28, move BL comma 43. This is numbers are stored in the AL and BL, and after addition, the result is available. Hexadecimal result is available in the AL. That hexadecimal result is converted into decimal number by using the DAA instruction. That's why it is used. That's why it is called as a decimal adjust after addition. Okay, so that is the thing.